Hi all, welcome to my second lecture on probability. In the first lecture, we had discussed a topic called conditional probability, and we had done a few exercises on conditional probability, and this was where we stopped in the previous lecture. Could you attempt this problem on your own? If not, we'll just see. The question goes like this: a die is thrown 3 times. Event A and B are defined as below. A is 4 on the third throw, and B is the event 6 on the first and 5 on the second throw. And you're asked to evaluate the probability of A given that B has occurred. Okay, so while attempting this problem, we need to know certain fundamental principles of counting. So the fundamental principles of counting go like this. Fundamental principles of counting. If something can happen in m ways, and another thing can happen in n ways, then both together can happen in mn ways. Mn ways. I'll tell you an example. You know what are the outcomes possible when you throw a die, isn't it? A die throw. The outcomes possible are 1, 2, 3, 4, 5, and 6. Now you just imagine the die is thrown a second time. Okay, so these are the outcomes possible when a die is thrown once. When you throw the die a second time, it is possible that you get again, it's possible you get all these outcomes. Now, if you look at the sample space of the event, that is, a die is thrown twice, isn't it? So, it's possible that you get the following outcomes. When it is a 1 on the first die, first throw. When it's a 1 on the first throw, you can have 1 to 6 on the second throw, isn't it? So you have 6 different possibilities coming in: 1 1, 1 2, 1 3, 1 4, 1 5, and 1 6. So this is true with 2 also. When you have a 2 on the first throw, you can have 1 to 6. Again, you will get 6 outcomes. Similarly, if you consider all the 6 possibilities in the first throw and 6 each for the second throw, you will get 36 outcomes, isn't it? So it's like in a single throw, a die can have 6 different possibilities. In the second throw also, it can have 6 different possibilities. Now, if you consider both these events together, that is, if you consider the outcomes for a die thrown twice, you have 6 into 6, that is 36 different ways of obtaining the number combinations. So, if you throw a die 3 times, here you are asked a die is thrown, you are given a die is thrown 3 times. So how many different outcomes will be possible? 6 into 6 into 6, which will give you 216 ways, which means your sample space has 216 outcomes. Okay, it is very difficult to enumerate all these possibilities. So now we'll just focus on what events we are interested in. So here you see A is the event where you obtain a 4 on the third throw. Okay, so what are the different possibilities you can think of? A is a 4 on third throw. So if you write down the sample space corresponding to the event A, we'll just see. So when you have a 1 on the first throw, you can have a 1 on the second throw, 4 on the third throw. When you have a 1 on the first, 2 on the second, again 4 on the third. Similarly, you can go 1 on the first, 6 and 4. So 6 different possibilities. Now when you have a 2 on the first, 1 on the second, 4 on the third, you can go like this up to 2, 6, 4. Then you write, okay, you can write all different possibilities. You can consider all different possibilities and you can write 6, 1, 4, 6, 2, 4, etc. to 6, 6, 4. Right. So these may be the different possibilities that you obtain favorable to the event A, where your event A is 4 on the third throw. Right. Now what's the event B that we are looking at? It is 6 on the first and 5 on the second. So you have two things which are fixed here. So the sample space corresponding to B is slightly more easy to write. So you have 6 on the first, 5 on the second, then you can have 1 on the third, you can have a 2 on the third, etc. You can have a 6 on the third. Right. You have 6 different possibilities. Now, what would be the probability of B? The probability of B would be there are 6 different outcomes. Out of the 216 outcomes, only 6 favor the event B. Now, is there something which favors both A and B? Yes, of course. You have an outcome here which is 654, which favors occurrence of both A and B. Right. You have an element here 654 in sample space B also. So the element which favors the occurrence of both A and B, the sample space is 654. So what is P of A intersection B? It's just one element out of the 216 which favors occurrence of both A and B, isn't it? So what was my question? My question was to evaluate the probability of A given that B has occurred. Right. Now, as per my definition, P of A given B is nothing but P of A intersection B by P of B. So I have here 1 upon 216 divided by 6 upon 216, which gives me 1 by 6. Okay. So the probability of A given that B has occurred, can be evaluated as 1 by 6. The basic principle that you need to remember in such problems is the counting method. If one event can happen in m different ways and another event can happen in n different ways, taken together, both can happen in mn different ways. Okay, so if it is so, we'll go to the next problem. It is slightly less complicated than the previous one. A die is thrown twice, and the sum of the numbers appearing is observed to be 6. Now you are asked to evaluate the conditional probability that the number 4 has appeared at least once. So, how many elements do you expect in your sample space? A die is thrown twice, right? In a single throw, there are 6 possible outcomes. In the second throw also, you can have 6 possible outcomes. And when you're considering the sample space for a die thrown twice, you should expect 36 points in the sample space. So your sample space S will contain 36 sample points. Now, let's focus on what event A is. Okay. You are asked to find the conditional probability that the number 4 has appeared at least once. So you need to know that. So let event A be the number 4 has appeared at least once. So what would be the sample space corresponding to A? You can have a 4 on the first throw. Then you can have all possibilities from 1 to 6 on the second throw, isn't it? And then you can have 1 on the first throw, 4 on the second, and you can have all possibilities like 2, 4, 3, 4, etc. up to 6, 4. Okay, now we also were given something else, right? The sum of the numbers appearing is observed to be 6. So let event B be that sum of the numbers appearing is 6. You know that in a die throw, numbers from 1 to 6 are possible. Here you have a die being thrown twice. So you are asked the different combinations possible such that the sum of the numbers appearing is 6. So if I write down the sample space corresponding to B, what is it going to be? I can have 1, 5, which gives me 6. I can have 2, 4, 3, 3, then 4, 2, and 5, 1, isn't it? So I have 5 different possibilities which give me a sum of 6. Now what is P of B? P of B is nothing but 5 out of 36. Why? Only 5 outcomes in the sample space is favorable for the event B. So my P of B is this thing. Now, is there something in the sample space which favors both A and B? Is there something common? Yes, of course. I do have a 2, 4 here and I have a 2, 4 here. I also have a 4, 2 here which appears here. So my A intersection B would contain 2, 4 as well as 4, 2. right? So there are two outcomes which favor occurrence of both A and B. So I will have P of A intersection B as 2 upon 36. Now, what's the conditional probability of A given that B has occurred? It is P of A intersection B by P of B, which is 2 upon 36 divided by 5 upon 36, which would give me 2 by 5. So I hope this topic of conditional probability is quite clear to all of you. Now we'll move on to something called the multiplication rule for probability. If E and F are events in a sample space S, and what do we mean by E intersection F? E intersection F means the set for occurrences of both E and F. ഓക്കെ, അതായത് ഇയും എഫും സൈമൾട്ടേനിയസ് ആയിട്ട് ഒക്കർ ചെയ്യുന്ന ഈവൻസിനെയാണ് ഈ ഇന്റർസെക്ഷൻ എഫ് കൊണ്ട് ഡിനോട്ട് ചെയ്തിരിക്കുന്നത്. ആൻഡ് വി ഓൾസോ നോ ബൈ ഡെഫിനിഷൻ പ്രോബബിലിറ്റി ഓഫ് ഇ given f has occurred is given like this: p of e intersection f by p of f. So from here, if you are to write p of e intersection f, you can write it like this, right? It is p of f times p of e given f has occurred. If you give equation number a to this relation, we can as well write a relation for conditional probability of f given that e has occurred. So that relation would be pretty much the same, except for the fact that in the denominator you will have p of e, because you are given that p of e has occurred, and out of that how many events favor occurrence of f also. That is what you are looking at. So your relation for conditional probability of f given that e has occurred is like this, and from here you can write another relation for p of e intersection f. Okay, so from a and b you can write that p of e intersection f can either be written as p of e times p of f given e has occurred, or the other way around, it is p of f times p of e given that f has occurred. Okay, this is called the multiplication rule of probability, which helps us evaluate the simultaneous occurrence of two events. Okay, so now we'll see an example for this. If you take a bag which contains 10 black and 5 white balls, and 2 balls are drawn from the bag one after the other, what is the probability that both drawn balls are black? This is your question. So you can imagine the picture. You have a bag with you and you have 10 black and 5 white balls, and you are pulling out one ball after the other, and you're being asked what is the probability that both the balls that you draw are black. So let's consider the event E. Let the event E be the first ball is black. Okay, so what are the total balls, number of balls in the bag? There are 15 balls. Okay, so the probability of pulling out a black ball would be 10 out of 15, because there are 10 balls which are black in color. And so P of E would be 10 upon 15. Now, what are you asked to find? You are asked to find the probability that both drawn balls are black. So the second event F that you are looking at is nothing but you are pulling out a second ball which is also black in color. Okay, now what changes have happened here? When you pick a ball from the bag, the number of balls in the bag reduces by 1 and it becomes 14. And now you're already told that the first one is black, then the number of black balls would also have reduced to 9. So P of F, given that E has occurred, I mean in the first pull അതൊരു ബ്ലാക്ക് ബോൾ ആണ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ പിന്നെ P of F given E would be 9 on 14. Okay, now we need to know the probability that both drawn balls are black, isn't it? So we need to evaluate the probability P of E intersection F, which tells us the simultaneous occurrence of both E and F. Okay, so that is nothing but from our relation, it is P of E times P of F given E, which is 10 upon 15 times 9 by 14. We can evaluate it as 3 by 7. Now, what if you are looking at more than 2 events? Then the multiplication rule would be something like this. If E, F and G are 3 events in a sample space S, then P of E intersection F intersection G, that is simultaneous occurrence of these 3 events. Okay, so that would be like the probability of E times probability of F given that E has occurred. Now you are given that E and F have occurred, then what's the probability of G to occur? So that would be P of G given E intersection F, because E intersection F just means all the outcomes which favor both E and F. Okay, so given that E and F have occurred, what's the probability that G occurs? Okay, so you can write this multiplication rule for as many events as possible. If you have a fourth event, it would be like say you have another event to H also, then you can write this probability as P of E intersection F intersection G intersection H, and that would be P of E times this term times this term times it would be P of H given E intersection F intersection G, because you are given that all the 3 events have occurred and you are looking at the probability of the 4th event to occur. So this rule actually can be written for as many events as possible. We will just try to understand this a bit more from an example. 3 cards are drawn successively without replacement from a pack of 52 well shuffled cards. What is the probability that the first 2 cards are kings and the third card drawn is an ace? Okay, so let's look at define the events. Let E be the event. First card is a king. Now what would be the probability? There are 4 kings in a deck of cards, so it would be 4 out of 52. Okay, now you are given that the first card is a king, so the number of kings would reduce to 3, and since you are not replacing the cards into the deck, the number of cards in the deck will also reduce by 1, which gives me 51. So the event F, given that E has occurred, would have a probability 3 out of 51. Okay, now that you have pulled 2 cards from the deck, the number of cards would be 50. And what is the third event that you're looking at? The third card drawn is an ace. Since you've pulled out only kings, the number of aces still remain at 4, but the total number of cards have reduced to 50. So the third event probability P of G given E and F have occurred would be 4 upon 50. Now what's the probability that all the 3 happen? That is, the first 2 cards are a king and the third one is an ace, would have a probability 4 by 52 times 3 by 51 times 4 by 50, which should be 2 outcomes out of 5, 5, 2, 5 outcomes. That's the probability of this event to happen. Okay, I hope it is clear. Now, let's also touch upon a topic called independent events. Now, as the name suggests, we will understand it uh, using an example. Consider an experiment of drawing a card from a deck of 52 cards. When you're pulling out a card, every card is equally likely and will have the same probability. Now, let E be the event that card drawn is a spade. What's the probability of E? It is 13 out of 52. Right, it's 1 by 4 because there are 4 different signs in a deck of cards, and there are 13 cards which are spades. Now, let F be the event that card drawn is an ace. How many aces are there in a deck of cards? 4. So your probability of F is 4 upon 52, which is 1 by 13. Now, what was P intersection F? E intersection F. E intersection F is nothing but events which favor occurrences of both E and F. Do you have something like that? That is, what is E intersection F here as per this example? E intersection F would be you are pulling out a spade ace, isn't it? So what's the probability of such an event? There is only one card which is a spade ace. So your P of E intersection F would be 1 out of 52. Right. From our relation of conditional probability, P of E given that F has occurred is defined like this. It's P of E intersection F by P of F. And on evaluating, I get it as 1 by 4, which is nothing but my P of E. Okay. So if I am taking a deck of cards and I am looking at these two events separately, each have a probability like this. P of E is 1 by 4 and P of F is 1 by 13. Now, given that something has occurred, what is the probability for the other event to happen? That is what I am looking at here. Given that F has occurred, what's the probability of E to occur? And I find that it is the same as P of E. Okay, I get it as 1 by 4. Now, what exactly should I understand from this? I should understand that the occurrence of the event F has not influenced the occurrence of E in any way. Okay, that's what I understand from this. Such events are called independent events. And for independent events, this is how your relation looks like. P of E intersection F, you had two relations from the previous slides. P of E intersection F can either be written as P of E times P of F given E has occurred. But if your events are independent, the occurrence of E has no influence on F, which means your P of F given E has occurred is P of F itself. Similarly, it can also P of E intersection F can also be defined like this: P of F times P of E given F. But just from this example that we saw here, we saw that P of E P of E given F has occurred. It's the same as P of E. അതായത് എഫ് ഒക്കർ ചെയ്താലും ചെയ്തില്ലെങ്കിലും പി ഓഫ് ഇയുടെ പ്രോബിലിറ്റി അല്ല ഇ എന്ന് പറഞ്ഞ ഈവന്റ് നടക്കുന്നതിന്റെ പ്രോബിലിറ്റിക്ക് പ്രത്യേകിച്ച് മാറ്റങ്ങളൊന്നും സംഭവിക്കുന്നില്ല. അങ്ങനെയുള്ള ഈവൻസിനെയാണ് ഇൻഡിപെൻഡന്റ് ഈവൻസ് എന്ന് പറയുന്നത്. അപ്പോൾ ഒരു ഈവന്റ് ഒക്കർ ചെയ്യുന്നത് കൊണ്ട് മറ്റേ ഈവന്റിന്റെ പ്രോബബിലിറ്റി ബാധിക്കപ്പെടുന്നില്ല എന്നുണ്ടെങ്കിൽ അങ്ങനെയുള്ള ഈവൻസിനെ ഇൻഡിപെൻഡന്റ് ഈവൻസ് എന്ന് പറയുന്നു. ആൻഡ് ഫോർ ഇൻഡിപെൻഡന്റ് ഈവൻസ് P of E intersection F is nothing but the product of the individual probabilities P of E and P of F. Okay. Ini, one point I would like to tell here is when you study probability, you may come across terms like mutually exclusive and independent. And I'd like to stress here that mutually exclusive and independent are not the same. Okay. Independent എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ രണ്ട് ഈവൻസ് നടക്കാനുള്ള സാധ്യതകൾ നമ്മൾ നോക്കുമ്പോൾ ഒരു ഈവന്റ് നടന്നതുകൊണ്ട് മറ്റേ ഈവന്റിന്റെ സാധ്യതയ്ക്ക് പ്രത്യേകിച്ച് മാറ്റങ്ങളൊന്നും സംഭവിക്കുന്നില്ല എങ്കിൽ അങ്ങനെയുള്ള ഈവൻസിനെയാണ് ഇൻഡിപെൻഡന്റ് ഈവൻസ് എന്ന് പറയുന്നത്. മ്യൂച്വലി എക്സ്ക്ലൂസീവ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ഒരു ഈവന്റ് നടന്നു കഴിഞ്ഞാൽ മറ്റൊന്ന് നടക്കില്ല എന്ന് വെച്ചാൽ ഇപ്പോൾ ഒരു കോയിൻ ടോസ് ചെയ്തു എന്ന് വിചാരിക്കാം. കോയിൻ ടോസ് ചെയ്യുന്നതിൽ നമുക്ക് പോസിബിൾ ആയിട്ടുള്ള ഔട്ട്കംസ് എന്ന് പറയുന്നത് ഒന്നുകിൽ ഹെഡ് ആകാം അല്ലെങ്കിൽ ടെയിൽ ആകാം. ഓക്കെ, ഹെഡ് ഒക്കർ ചെയ്താൽ പിന്നെ ടെയിൽ ഒക്കർ ചെയ്യില്ല. ഓക്കെ, ഒരു കോയിൻ ടോസ് ചെയ്തിട്ട് നമുക്ക് ഔട്ട്കം വരുന്നത് നമ്മൾ ഫേസ് ചെയ്യുന്ന കോയിൻ്റെ ഫേസിൽ ഹെഡാണ് വന്നിരിക്കുന്നത് എന്നുണ്ടെങ്കിൽ അതിൽ പിന്നെ ടെയിൽ ഒക്കർ ചെയ്യുക എന്നുള്ളൊരു പോസിബിലിറ്റി ഇല്ല. അതായത് ഒരു ഔട്ട്കം സംഭവിച്ചു കഴിഞ്ഞാൽ മറ്റേത് ഒരിക്കലും സംഭവിക്കില്ല. അങ്ങനെയുള്ള ഈവൻസിനെയാണ് മ്യൂച്വലി എക്സ്ക്ലൂസീവ് എന്ന് പറയുന്നത്. എന്നാൽ ഇൻഡിപെൻഡന്റ് എന്ന് പറയുന്നത് അങ്ങനെയല്ല. രണ്ട് ഈവൻസും ഒക്കർ ചെയ്യും, പക്ഷെ ഒരെണ്ണം ഒക്കർ ചെയ്തത് കൊണ്ട് മറ്റേ ഈവന്റിന്റെ സാധ്യതകൾ മാറുന്നില്ല. ഓക്കെ, സോ ദീസ് വേർഡ്സ് may seem the same, but they are not the same. Okay, mutually exclusive is something else, independent is something else. So if you are to check the independence of events, all you need to see is whether your P of E intersection F is P of E times P of F. So here I have an exercise for you. A die is thrown. If E is the event, the number appearing is a multiple of 3, and F is the event, the number is even, then find whether E and F are independent. And the hint is nothing else but just check if P of E intersection F is P of E times P of F. Okay. Two more exercises for you. An unbiased die is thrown twice. Let event A be odd number on the first throw and B be the event odd number on the second throw. Check whether events A and B are independent. Now the third exercise, 3 coins are tossed simultaneously. Consider event E as 3 heads or tails, and F is the event at least 2 heads, which means you can consider possibilities where you have 2 heads and more, and G is the event at most 2 heads. So you can consider all possibilities where you have no heads, where you have 1 head, and where you have at the maximum 2 heads. Now you are asked to find of the pairs of events EF, EG and FG which are independent. We'll have a discussion on these exercises in the next lecture. Thank you.